Okay, so just like how we use the first derivatives test to solve the local maximum minimum, we can actually use the second derivatives test to solve the same process. What we're stating is that for a local maximum or minimum to occur, it's going to occur where f prime of c is equal to 0 and f double prime of c is greater than 0, meaning that the slope is going to be 0 when the function is concave up. That's going to give me a local minimum. If the slope is 0, where it is concave downwards, that's going to give me a local maximum. Now, when we use the term f at c, c is our critical number. So this is just another shortcut that we can use. The second derivative test does not work when both the first derivative and second derivative are equal to 0. Then we'd have to actually just fully use the first derivative test to determine if there's a local maximum or local minimum using increasing and decreasing values. So if we try and use the second derivative test for these functions, then we're going to say that for the first function, f prime of x is equal to 3x squared, which means that my critical number is going to occur at x is equal to 0. The second derivative is going to be 6x, and this means that my significant number is going to occur at x is equal to 0. So in this case, f prime of 0 is 0, and f double prime of 0 is 0. When I graph out this example, right at that point 0, 0, it would be a point of inflection. It's not a local min or a local max. When I go to the next example, g prime of x is going to be 4x cubed, which means I'm going to have a critical number at x is equal to 0. G double prime of x is going to equal 12x squared, which means I'm going to have a significant number at x is equal to 0. Once again, we have the problem where f prime of 0 is 0 and f double prime of 0 is 0. But unlike the last example, when I graph this out, at that point 0, 0, it happens to be a local minimum. So our first case, it was a point of inflection. Our second case, it's a local minimum. In our last case, I have a critical number at x is equal to 0. H double prime of x is equal to negative 12, x squared. And I have a significant number at x is equal to 0. Just like the last two examples, f prime of 0 was 0, f double prime of 0 was 0. But unlike both the last two cases, now when I graph it out, it happens to be a local maximum. So when both our first derivative and our second derivative are 0 at a point, it could be a point of inflection, it could be a local minimum, it could be a local maximum. It is not enough to determine. For example 1, it says determine the maximum and minimum values of f of x is equal to x cubed minus 12x plus 5 using the second derivatives test. Well, when we think of our process, the first thing is I take a look at this function. It's a polynomial function, so I know it's going to have a domain of x, e, r. When I take the first derivative, f prime of x is going to equal 3x squared minus 12, which means that when I'm doing my critical numbers, 0 would equal, when I factor this down, 3x plus 2, x minus 2, which means that my critical numbers would occur at x is equal to positive or negative 2. When I take the second derivative of this, when I derive the 3x squared minus 12, it just becomes 6x. So I'm going to take the second derivative of negative 2, which is going to give me negative 12. And I can see that when I do it for the first critical number, f prime of negative 2 was equal to 0. F double prime of negative 2 was less than 0, which means there was a local max at x is equal to negative 2. It's going to be concave downwards, and it's going to have a slope of 0, local max. When I try the other critical number, f prime of positive 2, then it's going to give me positive 12. And in this case, I see that f prime of positive 2 is equal to 0. F double prime of positive 2, in this case, is greater than 0, so it's going to be concave upwards. Therefore, I have a local minimum at x is equal to positive 2, because it's going to be concave upwards, and it's going to have a slope of 0 at this point. When I'm determining the local maximum and minimum values, then I just have to take those points where I solved that there was a maximum and minimum and put it back into my original function. So I'm going to start by solving my local max. and that's going to be f of -2. So I'm going to sub it in, -2 cubed minus 12 times -2 plus 5 is going to give me 21. There's my local maximum. I'm going to solve my local minimum. Take f of +2, and that's going to give me 2 cubed minus 12 times 2 plus 5, which is going to give me -11. And then finally, I do my statement. Therefore, f of x has a local maximum value of 21 and a local minimum value of -11.